let's get started. It's my great pleasure today to introduce Karthik Bhargavan from INRIA, who's our speaker today. Karthik's a good friend and actually a former intern mentor from maybe, I don't know, Karthik, maybe, I guess it's kind of maybe 20 years ago or something, close to that. 16 years, 18 years ago, something.
You're going to show our age, you should say these things.
I'm really happy to have him here today. He's Karthik is a researcher at INRIA and leads the Prosecco team there, working on verified programming with secure programming with cryptography, and is going to tell us about some of that work today. Karthik's won many awards, too many to mention, and I'm really happy to have him here today. So, Karthik, it's all yours.
Thank you. I'm guessing you guys can see my slides, but all right. So thank you so much for that kind introduction, Nico. It's fun for me to give this talk. So the work I'm going to be talking about today is shared with too many people to mention. So just note that it's extremely collaborative work. Okay, so towards high assurance crypto software. So I think we're currently going through a golden period for the design and deployment of new cryptographic mechanisms and protocols in mainstream software. Some signs of this is that now most of the web is encrypted using fairly new protocols like TLS 1.3 and Quick. Almost all of us probably on this call are using secure messengers like Signal, or even if you're using WhatsApp, you're using the secure mode of WhatsApp. And of course, there's a ton of cryptocurrencies around, too many to mention. And that's just today, right? And then what's coming up? There's a ton of post-quantum crypto, and a ton of lightweight crypto for IoT devices. And each of these crypto primitives comes with its own protocols, new devices for new devices, and so on. So one way to look at this golden era is to be happy and say, yes, finally cutting edge crypto in mainstream apps, not just for big corporations and governments and military, but everybody can now enjoy strong security and privacy. But the glass half empty way of looking at it is, we have these new protocols, very much unstable, fresh code, subtle APIs, all based on academic crypto that nobody really understands very well. So how do we kind of address this moment? Well, I will advocate that what we need is tools and techniques for building high assurance crypto software. And that's kind of what I'll open the box on today. So let's take an example. So all of us are using probably Signal or some version of Signal. Many of us probably, and it's what is Signal? It's a messenger, which is an app on iPhone and Android. The nice thing about it is provides end-to-end encryption, which means you don't have to trust the server. Every message is encrypted on your device and only gets decrypted on your friend's device, wherever it might be in the world. And so even under coercion or any other kind of attack, nothing between these two devices should be able to read these messages, which is a great property to have. And so if you go look inside the internals of Signal, you'll see that Signal is extremely well documented. There's the X3DH key agreement protocol, the double ratchet algorithm, the Sesame algorithm. It's one of the best documented crypto apps you will see out there. All the code is open source. You can look at that too. Of course, this open source code, some chunk of it is also used in very popular apps like WhatsApp and Skype. So it has very high impact, but also is very open, very widely reviewed, many academic proofs and so on. So a priori, you might say, well, an important app like Signal with so much riding on it would be a great candidate for a high assurance implementation. So let's look at what the implementation of Signal looks like. So if you go look in the iOS app of Signal and you break down the code components in it, this is what you find. You find that about 90% of the code is what I would call user interface application level code. The crypto library part of it is about 1%. The protocol code is about 2%, and the key and the session handling is about 7%. So about 10% of this code is what I would consider security critical. Even that, though, is 30,000 lines. So the whole app is 300,000 lines. The rest of the code is more like app code, which is not which would be shared between many other apps. It's not really specific to security. So how do we take this breakdown? How do we interpret this? Well, positive way of interpreting it is great. We only need to verify 10% of the code, so that's fantastic. The negative is that, well, 10% of this code is still 30,000 lines, which is way more than many of us know how to verify. The other problem, of course, is that any bug in that other 90% probably could affect the 10% that we have verified. So we have to be a bit careful about that. So what's the way forward, right? So here's a approach. So suppose you could isolate the security critical code that I said, at 10% of the signal code base, 30,000 lines, inside this nice isolated container, which contains a crypto library, all the protocol messaging code, all the key management that you need around it, all the session management, and so on. So anything that you would consider security critical for messaging, you put inside this box. And then we write a formal specification for each of those boxes. So for the crypto library, this would basically be the mathematical spec of what the algorithm is supposed to do. For the messaging code, this will probably be a model which is derived from the signal specs or some protocol standard if you're not talking about signal. And for the key management and session API, unfortunately, these happen to be very app specific. So you'd probably want to write a spec for it just for your own app on what you intend to do with this for these boxes. But once you've written down this formal specification, which I'm not going to claim is easy, but you can do it, then we can ask the verification question. Okay, so we can ask two questions. One is the code correct? As in, does this code on the left, the blue boxes, do they conform to the green boxes? Okay, and this is a software verification problem in a certain way. And the second question we can ask is whether the spec that you've written down is secure. Okay, which means that if an implementation conforms to the spec, will it be secure against the security goals that we have set for this mechanism in question? So I like to separate these two questions so that you can sort of see the differences in the methodologies and the approaches that you can use for the two of them. And this is the kind of question that I'm going to consider here. Let's assume that you can make this security critical code. How do you verify it? Of course, although we will not consider this in the rest of the talk, this is a very important question to ask. How do you isolate this code, right? If you are in a well-typed language, then you might be able to use some type abstraction to kind of make these interfaces in a way that the code outside cannot affect the code inside. If not, maybe you can write some defensive wrappers. In languages where you don't have this available to you, you probably end up using something like enclaves, maybe something like secure compilation. There's a lot of exciting research in this area, but as far as I know, I don't see anything which I can apply today to secure something like Signal. In the discussion time, if some of you have some ideas, I'd be happy to learn this. So I still consider this an open challenge, but for now I'm going to assume it's solved and move on to actually verifying what's inside this box. So, like I said, there are two questions to ask: whether the code matches the spec and whether the spec is secure. So let's just look at the bottom part of the code, the crypto library. So it's the simplest question we can ask, the cleanest one. Does the crypto library meet its mathematical specs? Is the crypto correct? So how is crypto implemented today? Okay, so this is roughly how it happens. There is some kind of RFC or standard published by IETF or NIST. So this is the CHA 20 Poly 1305 RFC. It's already, I think, a little bit obsolete, but this is the RFC. So you look in the RFC and you find some pseudocode. Okay, and that pseudocode is written in some fake Python-like language. And you look at the pseudocode, and then maybe you can write down a C implementation or a Rust implementation of this crypto primitive. And for CHA 20, you can write it in about 100 lines. You can even write it in shorter lines if you really care to use macros and stuff. But let's say you're going to use about 100 lines of code to write this implementation. And it's portable, it's C, it works on all platforms. And it's reasonably fast, actually. It takes about between 4 to 9 cycles per byte, depending on what machine you are. And that's pretty good for an encryption algorithm. But of course, if you're going to be using this encryption algorithm as your engine for pumping data through your network, then you need it to be faster. So on your laptop, for example, most likely you'll have an Intel AVX2 compatible chip, which means that you can write assembly code which uses AVX2 SIMD instructions in order to speed this code up. And you can get about a 5x speed up on your laptop, which means the speed of CHA goes under a cycle per byte, which is pretty good. But of course, most of your clients might be using phones, and phones probably have ARM compatible chips. So you're going to have to write another implementation in assembly, which takes advantage of the ARM Neon instruction set. Does more or less the same thing, but for different sized vectors with different instructions, and you get a little bit of a speed up there as well. So you have a third implementation now, right? And then you say, oh, actually my servers have these brand new AVX 5 and 2 servers, and they can do 16 operations in parallel. So I want to write another implementation for Intel AVX 5 and 2 which is going to give me a 10x speed up. Okay, and before you know it, you have about a 20,000 line code base for just Cha-Cha Poly. Whereas we started off with a couple of hundred lines of code in C, now we have about 20,000 lines, and most of it is in pretty much unreadable assembly code. And this is if you go look at OpenSSL, the code for these, you will see that there's that much code that much assembly code in it, which means that this code is going to be pretty hard to audit, test, maintain. People who are writing the assembly code for one platform probably don't understand the code for the other platform. It's kind of it's a bit of a mess. And of course, the big thing that we are worried about at DS3 is this code correct? You know, because this is all low-level code written by hand. It's very possible that we have introduced a buffer overflow in it, or a timing leak, or an arithmetic bug. It's very possible. So we need to verify this code. Luckily, there's many approaches that have come up recently on how to verify code like this. So if you say, I want to verify the C code for Cha-Cha, or I want to verify the ARM Neon code or the Intel AVX2 code, there's a variety of techniques you can use, each for each implementation. And the basic idea is you take the algorithm pseudocode, and on the left you see there, you write a high-level spec. You extract a high-level spec in some language. It could be Galena for Coq, or it could be F-star, it could be EasyCrypt. And then you take a low-level implementation and you prove that this low-level implementation meets this high-level spec. And you can use EasyCrypt for this, or Whale, or F-star, or a bunch of tools like this. The result of this verification is either going to be positive, in which case you know that your code is functionally correct, it's memory safe, and for some of these tools, you also get this guarantee of secret independence, which means a certain category of timing side channels does not affect this code. So it mitigates a certain category of timing side channels by not branching on secrets and not and things like that. Of course, if your verification fails, most likely there's a bug, but it's also possible that your verification technique was incomplete. So there's a bunch of interesting and exciting new projects which do things like this. Some do it for C code, some do it for assembly. There's also some tools for Rust now for verifying this kind of code. So given a single implementation and a high-level spec, we can ask this question. So at this point, should we consider the problem of verifying crypto libraries solved? So to answer that kind of question, in fact, I'm going to jump into a series of Q&As, okay? And for each question I'm going to pose, I'm going to give an answer which is very subjective, what is in terms of what I believe, whether the problem is solved, whether it's still being worked on, or whether it's actually pretty far in the future for it to be solved. And I encourage you to kind of pose more questions of this kind or debate my answers on this. So it's very possible that I don't have the full picture on this, but this is my opinion. So here's the first question, okay? So you're an app developer, you need a portable C implementation of AES or SHA-2 or ECC or RSA, some classic crypto primitive. Can you get it? The answer, happily, is yes. Almost for all standard crypto algorithms, you will find some verified implementation of it that you can download, okay? And I've just listed some projects which have done this, but you can just go and download it and use it. In fact, I would say there's no excuse left for people to not use verified code at this point. Second question, well, okay, I downloaded the C implementation of some primitive. Now I'm going to compile it with GCC or Clang. How do I know that this compiler is not messing with the verification guarantees that you gave me for your C code? Can I be sure of that? The answer is, well, actually, no, you can't if you use GCC or Clang. You might get better guarantees if you use something like ComCert, but ComCert is actually pretty slow for cryptographic code. It's being worked on. There are new optimizations being added to ComCert, but at this point, I would say ComCert is too slow. So there is this gap. Furthermore, these compilers may not just mess with the correctness guarantee, they may also introduce side channel leaks that you work very hard to remove in your source code. And this is, again, an active area of research. There are several techniques you can use to prevent or check whether the compiler has messed up. But on the whole, no, we cannot give you a guarantee that the compiler is not going to mess things up. So that's the incompleteness of this step. So you might say, well, okay, I don't want to use the C code anymore. Can you give me assembly code for my favorite crypto primitive? The answer is yes. For several primitives on some platforms, you can download verified assembly code, but not for all the primitives you might want and not on all the platforms, because the amount of work required to model each instruction set is significant. And then verifying assembly code is a little bit harder than verifying high-level code. So the results here are mixed. So I'm calling this kind of work in progress in some sense. But for many of these primitives, the answer is a resounding yes. So then, OK, you say, well, that's for classic crypto. What about fancy new crypto schemes? I have this post-quantum crypto scheme or a zero-knowledge proof or a fully homomorphic encryption thing. Could you implement and verify this? The answer is, in principle, yes, because there is nothing fundamentally blocking you from going from what people have already done for elliptic curves and extending it to these new constructions, except if the math is particularly complex. And so if you're using a isogeny-based scheme and you want to prove some interesting properties about it, maybe that will take a PhD student a significant amount of time to achieve. But for simpler constructions, like say Frodo Chem and so on, you can already see that there are proofs, and other people are working on proofs of other post-quantum crypto schemes in various of these tools as well. So this is, again, it's work in progress, but fundamentally there's nothing blocking you. OK, so now let's get to the really hard questions. Suppose you say that you have your own new implementation written in whatever favorite language you have of a cool new crypto construction. Can you verify it? The answer is almost always no, unless you have a PhD in verification so that you really can understand what the tools are doing. And unless you're really willing to rewrite your code to help the proof, it's not going to work. You're not going to be able to verify the code that you've written for some new unknown crypto construction. On the bright side, though, various projects will be able to, you might be able to steal and reuse verified components from various projects, like for field arithmetic and this kind of stuff. But on the whole, no, this seems like we are still at the stage where experts can verify things, but not crypto developers. And the last negative question, for which we have very bad answers right now, is could you take this kind of crypto code that you verified and prove that it has no side channel leaks and none of the categories of well-known side channel leaks that people are worried about in crypto? The answer is only yes, only for the small subset of timing side channels, which can be prevented using secret independence. For most other cases, it's either work in progress or absolutely no, as in we have no idea how to verify provably that a certain side channel doesn't exist in the code. So this is a little bit on the negative side. So given this survey of where we are, well, what am I excited about? Well, to kind of turn some of those questions from maybe to yes, there are two projects that I've been working on with a bunch of other collaborators that really excite me. The first is HACL and the other is hacspec. I'm going to talk a little bit about these in order. At various points here, if you really have a question, maybe Nick, you can interrupt me, and I could stop. But otherwise, I'll just keep going. All right. So what is cool and new about HACL? Okay. So here's the problem that I'm particularly interested in these days, which is, like I said, for each primitive, we have like multiple implementations in crypto libraries, right? And we have good solutions if you choose one of these and you say, I want verified assembly for Intel AVX2, or I want a portable C implementation. How to verify it? I think it's reasonably well understood. But what if I want to verify all of them? I want to verify all these implementations, okay? Because I want to actually deliver a library of implementations where everything is verified. How do I do that? So the strategy that I like, we worked on this last year, it was at CCS 2020, it's called HACLXN. And the idea is quite simple. It will be very familiar to many of you. What you really want to do is to verify the code once and to compile it n times. So that's what a compiler does, right? But in this case, there's a slight twist. Rather than let the compiler automatically optimize your code, we are going to optimize the code ourselves in the source code. But you're going to do this in a generic way, because the observation is that a lot of the speed benefits of these multi-platform implementation comes from using fairly generic strategies based on SIMD vectorization, parallelization. So here's the idea. We'll write generic SIMD crypto code in F*, where we don't actually care about what the size of the vector is. We just write it in a generic way for any vector width, whether it's 128 or 256 bits or 512 or whatever. And then we verify the generic code once and for all using typing in F*. So we prove memory safety, correctness, side channel resistance, and so on. And finally, just after the verification, before compilation down to C, which is what we do in HACL, from F*, we specialize and compile the implementation for each target architecture. So by the time the C code comes out, it is exactly for one target architecture it's specialized. But the source code and all the proofs are very generic. So this particular technique uses really heavily relies on advanced features of STAR, including specifically verified metaprogramming. And at the end, the code that comes out of this pipeline only works because we are able to use these compiler intrinsics for SIMD instructions, which are available and made available by most modern C compilers. So what is the verification workflow? So we start from an RFC-based formal spec, which you have to write in STAR by hand. And then we encode the parallelization algorithm as another spec. So we write a generic vectorized spec. And it's generic because you can instantiate it and get back the same spec as before, or you can use it in a vectorized way and you get many different implementations. So it's a generic vectorized spec. And you prove that this generic vectorized spec, which is implementing a parallelized algorithm, is correct with respect to the formal spec that you started off with. Okay, and this in some sense is the hardest part of the proof. And to do this, you have a whole access to a library of SIMD constructions with lots of nice lemmas that have been proved for you. So some of this proof is fairly generic, but some of it might be very specific because you might be putting in particular optimizations for the particular primitive that you're trying to parallelize here. But once you've parallelized the algorithm at the algorithmic level and proved it correct, the next step is fairly idiomatic. So you then write an implementation in the subset of F-star called low star, which is stateful, which is an implementation of the vectorized spec. And then you prove that this implementation matches the spec. And this is fairly boilerplate work. It still requires some work to be done, but mostly it's quite simple. And as a result of this verification, you get the code that your low-level implementation is functionally correct, memory safe, and all this stuff. And once you've done these verifications, you can compile down the low star code, and from the compiler, you get multiple implementations get spit out. Okay. So at compile time, you specialize the code to different platforms. So you get out a normal portable 32-bit implementation, which you would have gotten normally. And you also get implementations for AVX2, AVX, AVX5 and 2, ARM Neon, and so on. Okay, you get like 5 implementations out of this pipeline, even though you verified only one. So what is this? What is the proof effort? What does this parallelization step look like? Because that's the most interesting part of this pipeline. So let me just give you a little flavor. And before that, I'm assuming that people know about F-star, but if not, go check it out. It's a very cool programming language and verification framework, and all the work I'll be talking about today relies in some way or the other on F-star. Okay. So how does this parallelization of this step work? So here, for example, is the SHA-2 is the central shuffling function in SHA-2. Okay, so one round of the SHA-2 compression in the hash function. It has an internal state which is 8 words, but the words could either be 32-bit words or 64-bit words depending on the variant of SHA-2. So when you try to formally specify this algorithm in F-star, this is the specification looks like the one on the left. So we define a word type, which depending on which variant of SHA-2 you're using is either going to be a uint32 or a uint64. So note that this kind of branching on the definition of the type, we're already getting into things that can be done only in certain languages and not in other modeling languages. And then we define a state as basically 8 words. Okay, so it's already parametric on the variant of the SHA-2 algorithm we're going to be using. Okay, so once you've written that, you can then write operations like this. The CH operations is a certain kind of shuffling operation on words. And you can write the whole SHA-2 algorithm basically on the state. Okay, so let's assume that you've written it. How are we going to vectorize it? So SHA-2, we're going to use a very simple vectorization strategy, almost a naive, dumb one. We're going to run 4 SHA-2s in parallel. And the way it works is that you have 4 SHA-2 states. We're going to transpose them so that although we had 4 arrays, we're going to transform them into an array of vectors where each vector has 4 elements. And then we're going to apply the SHA-2 compression in parallel on all of these 4 elements of each vector until we get the final result. And then we're going to untranspose it or inverse transpose it back to get back the final 4 states. Okay. And that's the strategy we're going to use. And what does it look like in the level of specs? So on the left is the high level spec we wrote before, and on the right is the vectorized spec. So the first step is you replace every scalar type that you had in in your spec with a vectorized type, where the vectorized type basically is when you had an array of integers, now it's an array of vector of integers. Here we are defining all our types parameterized by a width, saying what is the width of the vectors. And we're saying that we'll support 4 different widths. If this is random, I could have added, we could have done 8 vector widths or an arbitrary number of vector widths, but these 4 are the most useful, so we're using these 4. And note that vector width of 1 basically means scalar. So this includes the scalar spec, but also generalizes it to work for vectors of arbitrary width. So then the next step is to take every scalar operation you had and replace it with a vector operation. And this syntactically is a super easy thing to do in F-star, because you have notation where we basically have vectorized versions of each operation. You just replace a scalar operation here with the vector operation. So the left to the right, it basically is a trivial change. And there are lots of lemmas that prove that, in fact, the function on the right is basically a map of the function on the left. And finally, when you're going to compile this code out, each of these operations, these vectorized operations, are not going to remain like this. They're going to get specialized for the SHA-2 algorithm and for the width that you're using. And the C code that comes out is actually going to be a vectorized operation for a particular width on a particular platform. And the last step, of course, is a proof. So you have to, after you've rewritten the entire spec like this, you're going to have to prove that, in fact, if you start from n SHA-2 states and you transpose them to get the vectorized state, you run the vectorized SHA-2 on it, and then you inverse transpose back, then you're going to get n results, each of which is a 1-by-1 SHA-2 of the original n inputs that we started off with. And this kind of thing is the classic kind of proof that we do. And of course, SHA-2 is the easiest example here. There are other algorithms for which the vectorization strategy is a bit more involved and you have to do a bit more work. So HACLXN is basically a collection of implementations that we have vectorized. So from HACL star, we took the implementation, we vectorized them. So we vectorized 8 algorithms, actually 4 families of algorithms, which total 8, for 5 different targets. So portable C, as well as AVX, AVX2, 512, and OmniOn. And for some of these algorithms, these were actually the first vectorized implementations, okay? Verified vectorized implementations. For some of them, they were even the first vectorized implementations on some platforms. In terms of proof effort, I think we have a win here, because we wrote 4 implementations and we got out 24 optimized implementations. So we actually got that, the thing that we started off with, that we got verified implementations for each platform, which are optimized for each platform from one after doing one proof, rather than having to verify each of the assembly implementations individually. But of course, the proof is in the performance, right? So if you don't get performance, what's the point of doing all this? And the performance is pretty good. So you get speedups like you expect for using vectorization. On AVX2, you get between 4 and 5x. On AVX5 and 2, between 7 and 10x. And so for many of these algorithms, you get very good speedups. For some algorithms like Blake 2, the speedups are less. On some platforms like ARM-Neon, the hash functions do particularly badly. And this is a well-known issue for all implementations, not just ours. So how does it compare to hand-tuned assembly for each of these platforms? So if you take Chacha 20 Poly 305, one of the fastest implementations is actually a verified implementation using Jasmine for AVX2. And our code is about 3 to 5% slower. Okay, so there is a 3 to 5% gap there. For SHA-2, our gap is a bit higher with OpenSSL, because OpenSSL assembly is really highly tuned, and it's about 9%. Our code is 9% slower on AVX2. But on AVX5 and 2, our code is faster, because SHA-2 actually does not optimize for that platform. OpenSSL doesn't optimize SHA-2 for that platform yet with the same strategy. So there is still a gap with assembly. Why is this? Okay, well, to an extent, you might say it's completely unsurprising. We are compiling code. We are not hand-tuning assembly code. So why should we expect to meet hand-tuned assembly code? But we still got within 3 to 5%. But there is that little 3 to 5%, and that gap there is exactly the place where assembly optimizations cannot be replicated in C code. Because, for example, you might be able to stitch or interleave 2 sequences of operations in a very clever way to avoid spilling of registers, and this is something that you really cannot see in the C code in a way that you would actually be able to exploit it. And then but that is just 3 to 5%. But the bigger gaps come when in fact you're not using certain instruction set features that are available, but you're not actually seeing them in your source language. So one example of this is the Intel ADX and BMI2 instructions, which are actually which can speed up multiplication by about 25%, but GCC Clang, these compilers don't use them and don't expose them. Okay, so those are the ones that really can make a difference. On the right-hand side here, you can see the verified whale code for 256-bit multiplication. Okay, so you can. So if you look at the code on the right here, it's basically using ADX2, ADX and BMI2, and these instructions are not available to see. And if you use this verified code, this is from the Whale project, you can get a 25% improvement. So the question that we can ask next is, well, okay, so for certain primitive, for certain routines, for certain subfunctions, you clearly need verified assembly. Can you combine this kind of verified assembly routines with other code which is written in C, because it's easier to verify code written in C, and then compose them together? The answer is yes. And this is a project called Evercrypt, which is a crypto provider that combines verified assembly from Whale with verified C code from HACL*, and it uses F* to unify the two of them, and the two of them have shared the same spec. So that's what they use. Okay, so put together, they are able to get best-in-class performance. So for example, for Curve 25519, combining code from Whale, combining code from HACL, you get performance that is better than any verified or unverified code for Curve 25519. At the time of publication, it was true. I think it's no longer true because there are newer implementations that use other features. All right, so HACL, Evercrypt, HACLXN, all available in the HACL* code repository. You can go try it out. And of course, it's also been widely deployed. It's in Firefox, in WireGuard, in Tezos, in Election Guard, and so on. So this is a project that is kind of a flagship project in my team, and we're kind of very proud of it. All right, so let's go back to the first picture that I had. I said, okay, you can verify code by writing a high-level spec, and then check that the implementation actually matches the spec, right? These specs, who's writing them? Because they are trusted specs. If there's a bug in the spec, then in fact your implementation will faithfully follow that bug. And so there is the guarantee that you're getting is only that your implementation matches the spec, not that the spec is correct. One might imagine that specs are probably easy to get right, but in fact, just in the last year, we probably have had 3 bugs in our specs. Well, the good news is that every time we found a bug in HACL*, it's been a bug in the spec and not a bug in the in our verification methodology, but a bug in the spec is still pretty annoying. So in practice, what happens is that each of these specs is written by hand for each tool. So depending on whether you want to use Coq to verify something or EasyCrypt or F*, you're going to write your own spec in the appropriate language and probably also tune the spec so that it helps you prove your code correct. So if you ask the question, is these specs correct? Well, first you must ask, are they even testable? Can you even test that they are passing the test vectors of the RFC? And the second question you might want to ask is, well, okay, for the standard crypto, which has actually got a nice specification and test vectors, maybe we can test the spec. But what about brand new crypto that cryptographers are just coming up with and they want to write a high assurance implementation for? Well, there's no test vectors or standard for this. So how do we make sure that these specs are correct? Can the cryptographers themselves write these specs? And if they cannot write these specs, can they audit these specs? Unfortunately, the answer is for many of these tools, the kinds of specs we are writing is actually not readable. You know, they're sort of readable for us, but not readable for people who actually know crypto even. So there is a bit of a gap there. So the gap we're trying to fill by this other project I'm very excited by called hacspec, which is a domain-specific language for writing crypto specs. So the observation is that over the last few years, Rust has emerged as the language of choice for new crypto software. So you can see there's a bunch of new crypto libraries, protocols, blockchains, zero-knowledge proof systems, all being written in Rust. And it's a good idea because, you know, if you get memory safety, you eliminate a large source of bugs in cryptographic software. So accepting that Rust is now the language of choice, here are two goals if you've set out for HACspec. First, can we get Rust crypto developers, as in people who are not verification experts, but who know sufficiently about crypto to write these kinds of implementations? Can we get them to write formal specs? In the goal being to reduce the gap between what devs understand, what they want, what their requirements are, and what the crypto verification tools provide. And accepting the reality that we are very far from the stage where a Rust crypto dev can directly use the crypto verification tools that we've been talking about. A second goal is to say, well, the other problem with a lot of our verification tools is that we have one proof in Jasmine, and for one primitive, a different primitive is verified in HACL and F***. How do we compare these proofs and how do we compose these proofs? If I want to take one verified primitive from here and a different verified primitive from somewhere else, how do we put them together when even the specs for these primitives are written in different languages? So can we write a single formal crypto spec that will actually be processed by multiple tools? So that's the idea behind HACspec, which is a language for writing these kinds of shared common specs in a way that even a crypto dev can write it. So this is the workflow we imagine for people using HACspec. So you start off by someone writing an application, and in the application he needs some crypto. So deep inside it, there is some crypto modules, but instead of actually using real crypto, because this might be experimental, fresh new crypto, we encourage the person to write this crypto as a spec in HACspec, in this language called HACspec, which is a subset of Rust. So you look at the crypto standard, you write these specs. So now you have an executable prototype application that you can run, you can test, and so on. And after having done that, you take your HACspec, which you've written, and you compile them to formal specs in F* or EasyCrypt or Coq. Right now we have an F* backend which is working, an EasyCrypt backend which is almost working, but the other ones are still to do. And once you have this formal spec, you can verify it against optimized code in Low Star or in F* or in Jasmine for EasyCrypt. And if the verification fails, you get the usual feedback. If the verification succeeds, you can then run your compiler to get out your C code or assembly code. Take the C and assembly code that you get, wrap it within Rust bindings, and then use that as a drop-in replacement for the crypto spec you started off with, so that you have transformed now your prototype Rust application into a production-ready Rust application with verified crypto inside it. So this round trip of starting with a spec, compiling to a formal spec, verifying the code, compiling the code, and putting it back in Rust. We've done this for a couple of primitives in HACL star, but we think that this is the way forward for new crypto constructions and primitives, that rather than sort of trusting the verification tool authors to do everything, I think this allows us to inject the crypto devs into the workflow of verification in a way that might have good results in the future. So what does HACspec look like? Let me give you a taste. So this is one function of a spec of the Cha-Cha-20 spec. Every function in HACspec, even though this is Rust syntax, this is Rust, yeah, because HACspec is a subset of Rust. Every function is purely functional. It has no side effects. Okay, so you cannot modify any external pointer. However, locally within a function, we allow you to modify local state. And this is just for convenience. It allows you to write nice specs that way. But the function is observationally pure. On the outside, you see no side effects at all. Then to write code like for elliptic curves, for big nums, for poly 1, 3, or 5, these kinds of mathematical cryptographic primitives, we provide a few high-level math constructs like a nat mod construct, which is basically natural numbers modulo some constant, and in this case it's modulo the modulo value given down there, which happens to be 2 to the power 130 minus 5. And once you do this, you basically get a type which is a copyable big num. So you never have to worry anything about the Rust borrow checker or anything, because all the time you're working in a purely functional world where everything is copyable. Even your arrays are always copyable and immutable. So you have a way of declaring arrays which are copyable and immutable. And so you can write your spec in a style that you would write in pure F* or Coq, for example. But this isn't Rust syntax. The third feature here that is of interest is that we provide a crate for secret integers. Where secret integers are just like integers, but they're used with capital U instead of small u, for example. And they have all the operations on integers except the ones that we deem dangerous. So you cannot take a secret integer and compare it. There's no comparisons, therefore there is no branching. You cannot use a secret integer as an index into an array. So the secret integers, which are enforced using the Rust type system, allow us to establish a secret independent discipline, which is like a constant time coding discipline. And this particular crate you can use in any Rust code, not just in hacspec. Okay, so even the high-level math stuff you can use in any Rust code. So these are the kinds of things that we provide in hacspec to make writing specs easier. And we've written a bunch of specs. Of these, the first two, for example, which are CHA20 and Polygon 305, we compiled to HACL specs and we proved them equivalent with respect to the HACL specs. Manuel Barbosa has also compiled them to EasyCrypt and proved them equivalent to the EasyCrypt specs of CHA20 and Polygon 305. There's also some post-quantum crypto that we have modeled in hacspec, and there's been a nice contribution of a pairing-friendly curve from Arhus that is also in hacspec. So there's a bunch of code that we've written in hacspec, but it's actually a very active project looking for contributions. So go to the website. If you have any cool new crypto you want to model and you want a formal spec for in FStar or EasyCrypt or Coq, this might be the nicest way for you to get it. All right, so this is the next natural stopping point for me. If there were any questions, if not, I'll just motor through.
Karthik, there's some questions about hacspec, and maybe it makes sense to take some of them now.
Yep.
So Alfonso de Gregorio asks, how does hacspec contrast with Cryptol, targeting Rust instead of Haskell?
Haskell.
So I think the question is that Cryptol, if I were to interpret it a bit, Cryptol seems to have some of the same goals as hacspec, but provides a Haskell-like syntax as opposed to a Rust-like syntax to write spec.
Right. Indeed. So there are several languages which sort of have the similar goal to hacspec. But in fact, we are in touch with some of the Cryptol developers, and we do hope that hacspec can also be a front end from which we can compile down to things like Cryptol specs. One thing that I believe fundamentally is that when I think we have put specs at too high a pedestal, that only like purists can write specs, which is actually very harmful for verification, because we think we want people who are writing the code to write specs. And using a real world language like Rust with its IDEs and its programming workflow, I think is the right step for getting developers to actually be able to write this kind of stuff. So I'm looking at hacspec as the way to get verification into the Rust developers workflow, which Cryptol doesn't actually aim for that in this particular case. I hope that answers the questions.
Yeah, Alfonso says thanks. Dave Nauman asks, is the hacspec subset only safe for Rust?
Yes, it's only safe for Rust.
And Barry Bond asks, is it feasible to translate Lodestar into Rust instead of C to enable building pure Rust apps instead of a mix of Rust and verified crypto in C?
Yes, it is conceivable. Of course, what that would mean is that, well, Lodestar is basically a subset of FStar that reflects a C-like memory model. You'll need a different subset of FStar that reflects a Rust-like memory model. And there is an ongoing project in the FStar community called Steel, which may end up, allowing us to do this kind of thing, which is to compile to Rust. Having said that, I find it kind of useful to have the two worlds side by side, because in a way, what this round tripping allows us to do is to have C and assembly code safely integrated into Rust. So it's in Rust, technically it's unsafe because we are actually integrating non-Rust typed code into Rust, but it has been verified at even a higher standard than the Rust type system. So I think this allows us to actually mix and match code in a safer way. So I'm actually excited about both sides of things.
I'm actually curious about the hacspec implementation. Are you able to leverage the Rust compiler internals to translate from hacspec to other languages?
Yeah, so Dani Merigu, my student, is the person who's really driving hacspec, and he's really he's let's say fighting with the internals of the Rust compiler to get the right place at which to hit this. So there's a lot of design choices on which AST to pick, and so on. And so there's a longer discussion there, but yes, we are able to utilize at the moment at least the Rust compiler to give us enough information. But this only works with Rust nightly at the moment for that reason, because we are really using the most advanced features that are available from the Rust compiler.
I'll just take one more question on hacspec. Do keep the questions coming, and we'll get to them towards the end of the talk as well. But last question for now, Mike Dodds asks, do you envisage other spec languages for other crypto implementation languages, for example, a hacspec for Python or Java, etc.?
So it's a good question. So from one spec to rule them all, we get to multiple specs again. But the original version of hacspec was actually in Python, and the reason was we looked at all the code that people were putting into pseudocode that people are putting into RFCs and specs at the IETF, and all of them were in sort of pseudo Python code. And so we said, okay, let's try to replace the pseudocode that people are actually putting into these RFCs right now. And we had some success. Dan Bernstein liked hacspec, so he actually uses it to specify Gimli, I think, in the official spec. But there wasn't so much pickup, because I think in the end, writing a spec in a language like Python, which looks like Python but actually isn't Python, just for the purposes of putting it into an RFC document, is a very, very niche thing, which only 3 or 4 people can actually do in some sense, right? So, and it's yet another artifact for you to maintain alongside your other implementations, because you already wrote a reference implementation in C, you already maybe wrote an implementation in Rust and so on. So that I would say that project was a very interesting one, the first version of hacspec, but a bit of a failure in that it didn't get picked up. Since we have started using Rust as a subset, already there's been a lot more contributions to hacspec than there was in the first round. So my feeling is that just the excitement around people already programming in Rust for these things, getting them to write the specs also in Rust, I think works very well. So I don't for the moment see going back to Python or Java or whatever, but indeed, so this is a multi-language question, and we don't know how it will evolve in the future. So shall I?
Yeah, do go on, and there's more questions coming in, but we'll save them for the next pause.
Okay, so I don't have humongous amount of time, so I may not get through all the things I wanted to say, but it's fine. So the next part of the talk was really saying, okay, so we saw a lot about crypto, hacspec, and HACL and so on, but really, like I said, that's only 1% of the code base. 9% of the code base is this thing on top, which you can roughly call the protocol code, but it's a combination of protocol code, key management, session management, that stuff. So how do we verify this, right? So the perhaps the most advanced example and sort of an illustration of the state of the art here is what I call the TLS 1.3 experiment. So between 2014 and 2018, for about 4 years, the IETF was designing this new protocol called TLS 1.3, and it actively sought the intervention of the academic community, actively sought proofs of the protocol before it was going to be standardized. And this resulted in a very vibrant community and research output from many people in different parts of the provable security realm. So there were proofs, of course, of various drafts of the protocol. There's also mechanized crypto proofs in CryptoVerif, and automated symbolic proofs of the protocol with Tamarin and ProVerif. And there was some verified implementation code which continues to be built in Istar. So on the whole, this kind of gave us a pretty good idea of what you could achieve with the current state of the art in both pen and paper proofs and mechanized proofs, right? So let's take this as a given and say, well, could you use this to solve our problem that we set in the first part of the talk, which is can you verify signal or the protocol core of signal using some of these techniques? So let's return to signal, right? So what does the signal protocol actually look like? If you go and unpack all the documents, what you see is that there's actually a fairly novel, what is called an asynchronous continuous key exchange protocol inside it, which is a composition of several sub-protocols, including something called X3DH, which is initial key exchange, something called a Diffie-Hellman ratchet, which provides this fairly novel and interesting property called post-compromise security, something called a hash ratchet, which provides forward secrecy, and authenticated encryption for message encryption and message security as usual. And all of these get composed in some interesting way to give us all the security goals that we have actually set for Signal. What's interesting about Signal is also inherently recursive, as in there is an unbounded number of rounds and each round ratchets over the previous round. So the security of a particular message is not just dependent on the key right then, it's dependent on a chain of keys that led up to this key. Okay, and the chain could be unbounded length because it's actually a recursive protocol. And that makes it interesting because now you can ask, well, okay, can you actually even verify this protocol? It's sort of fairly novel. It's using all these sub-protocols which are fairly novel. And can you prove that its implementation is correct? So how do you model this protocol? So the protocol can be written down roughly on like it looks on the right. Of course, there's a loop in the protocol which I'm not showing here, but basically the protocol keeps repeating. The bottom part of the protocol can keep repeating any number of times. So if you just focus on the first part of the protocol, it's basically between an initiator and a responder. Initiator initially knows its own keys. The responder has 3 keys, not just one. And to initiate the protocol, the initiator uses the responder's public keys and does a bunch of Diffie-Hellmans to exchange to first send the first message. In fact, before you send the first message from the initiator to the responder and signal, you do 5 Diffie-Hellmans even before the first message. And each of those Diffie-Hellmans is provides a slightly different guarantee and has a different security goal. And mixing all of those 5 Diffie-Hellmans together gives you a certain guarantee which you start off with in Signal. And that's the starting point. This is just the first message. So at a certain level, it looks complicated, but at a different level, you can say this is all just standard stuff. This is standard crypto. It just happens to use a lot of crypto. So just like we write specs for crypto algorithms like curve 25519, you could write a spec for each of these functions fairly easily. You could write a function for the initiate, you could write a function for the next step and so on. And once you write those functions, proving that an implementation meets those functions or that those functions are secure becomes the next step. So to prove the security of Signal in Euro S&P 2019, we wrote a model of Signal both in ProVerif and in CryptoVerif, where ProVerif uses a symbolic abstraction of crypto, which means it can analyze for logical flaws in the protocol, but not for problems regarding how you used or misused the crypto assumptions. Whereas CryptoVerif uses a very precise computational model of crypto primitives. When the side effect is that since ProVerif uses a high-level abstraction, it's more automated, whereas CryptoVerif is less automated, right? But even so, since this is a recursive protocol and the key material effectively keeps growing with every round, the proofs for this protocol in ProVerif and CryptoVerif were limited, very severely limited to just 2 or 3 messages. Okay, so 3 message maximum. After that, the machine would just give up on this kind of proof. And there was no, at least we didn't discover a very easy way of doing an inductive proof in a way that would be suitable for these tools, because these tools really do not support induction. And that's a place where a lot of these automated verification tools or even semi-automated verification tools come to a stop. This is where tools like Coq and F-star can win because they actually support general forms of induction. Okay, so let's assume that we have actually proved Signal. We haven't, it's a very severe limitation, but let's say we have done it. So how about verifying the protocol code for LibSignal? Well, that's been done as well. So in S&P 2019, we wrote a low star implementation of the components of Signal on the left. We wrote a spec and F-star and we proved that they were correct. Okay, so and as a result of that, what you get out of that is an implementation of Signal, which is in C. You can also extract this implementation of Signal, which is in WebAssembly, using the F-star compilation architecture, which is the Kremlin compiler. And that compiled code you can embed back into the official LibSignal JavaScript package to obtain a drop-in replacement of LibSignal that you can use in any application that relies on LibSignal, but now uses verified crypto and verified protocol code on the inside. To isolate this verified code from the rest of the code, we try to write a defensive wrapper in JavaScript. It provides certain guarantees, but not really as strong as you might imagine or might want. OK, so we've managed to verify that the code for this core of Signal meets a spec for the core of Signal in F star. We've managed to verify in using ProVerif and CryptoVerif that the protocol model of Signal is secure, but there's a gap. There's a gap between these specs because, of course, there was something was in F star and something is in CryptoVerif. So there's a sort of you can sort of compare the two and say, well, they're more or less the same protocol, but there is a formal gap. But what is worse is that the proof in ProVerif and CryptoVerif is very limited. It's only for 3 rounds or 2 rounds, for 2 rounds in CryptoVerif and 3 rounds in ProVerif. So this is a very limited proof that we're getting out of this. So that's kind of the place where we are, where we were, let's say, until last year in terms of what we could do with LibSignal. So at this point, it's worth pausing and doing that same exercise we did with crypto libraries to say what is the state of the art for what can we do with protocol verification today. So we've seen TLS 1.3 was very successful. We've seen with Signal we can do certain things and we stopped at certain places. So what is possible and what is not possible today? So here's the first question. I have a new secure channel protocol, say, and I want to verify it against some realistic class of threads. Can you do it automatically? The answer is yes, if the class of threads you're thinking about is a symbolic or $yao class of threads, which is the class of threads which can find all kinds of network attacks, man-in-the-middle attacks, and so on, but not really go down all the way to the details of the crypto primitive. And you can use tools like Tamarin or ProVerif to do this. And like we already saw, there are limitations when you come to recursive protocols. There are other limitations if you're dealing with group protocols and so on. But if you're doing a standard secure channel protocol, most likely, yes, you can verify this automatically. What about if I want to build a mechanized crypto proof for my protocols? This is also possible because there are tools like CryptoVerif, there are tools like EasyCrypt, and other tools which use theorem provers to do this kind of proof. But the proofs are semi-automated in the sense that you need to provide quite a bit of human intervention to achieve these proofs. So I would say this is still in the range of, well, you probably need to have some verification expertise. You can't just push button this to make this work. You probably need to have some crypto expertise, some verification expertise to make these tools really work today. But then that was for classic protocols. What if I have a brand new protocol that uses zero knowledge proof system, multi-party computation, group key exchange? No, we are not that will not be so easy for you to verify right now. I mean, there's many ongoing work. So this is an orange for me. There's many pieces of work which are happening right now, which might help us do this systematically in the future. But for now, these are really a little bit out of reach. So then let's move to the code side. So those are all for the protocol design. But can I verify that my protocol code is correct with respect to my spec? This is just standard software verification. So yes, you can. In fact, there are very successful projects. One is called EverParse for verifying packet formats. You can verify state machines. You can verify like the LibSignal code I showed you. You can verify the protocol code. You can verify lots of interesting components in your software using standard software verification techniques in F-star or other tools. But let's go to the hard question. Can I link my protocol code to a security proof? As in, can I close that missing link between what I verified for functional correctness and what I verify for security? This is still a bit of work in progress. So there is a kind of successful project that I'm part of as well called MeTLS, and it's part of the Everest group of projects where we use code-based crypto proofs to verify protocols. But this is quite hard because you need to have expertise both in crypto and in verification to achieve these kinds of proofs. So far, this kind of effort has only been worth it for important protocols like TLS 1.3. If you just take any new protocol that you wish to analyze in this way at the code level, I would say this is still a pretty hard task. Finally, let's come back to the question that we started off with. Can I verify the Signal security core, which is 30,000 lines of a mix of languages, but a lot of which is in C? No, it's too large. Our tools don't scale. We can't verify 30,000 lines right now. But if you allow us to rewrite the code and replace it, then maybe. Okay, then we can probably do it. And this is kind of the idea where we already did the LibSignal, where we rewrote things in F star. Maybe we can do it. If you rewrite it in Coq, you can do it. So if you allow the verification guys to rewrite your code, then maybe you can do it. So that's the idea here. So let's close that gap with LibSignal. Let's finish this talk with an optimistic thing. And instead of using a different tool like ProVerif or CryptoVerif to do the security proof, what if we used F star itself to do the security proof too, completely eliminating that gap? Furthermore, maybe using F star, we can do the full crypto proof for any number of rounds. That would be great, right? So we eliminate the gap in the proof and the gap in the models. So for this, we're going to use this recent work that we just published at EuroSNP this year, which is not even published, let's say, it's going to appear, called dy star, which allows us to do scalable symbolic security proofs for F star code. The basic idea between dy star is that it's structured in 3 different layers. At the bottom, we have a concrete trace-based symbolic runtime model of protocol execution, which is coded up in F star. Then on top of this, we develop labeled abstract APIs for crypto, for storage, for all the protocol actions in F star, which abstract away from the details of the low-level runtime model and provide nice security abstractions that are easier to verify protocols with. And these are proved sound once and for all, okay, these abstract APIs. And once you have these abstract API, you can verify each protocol individually, fairly simply, I would say, for security. So this is concrete executable protocol code that you've written, and you can also verify it for security. Okay. So what does dy star code look like? Well, I don't expect you to read the code on the left, but here are some features of it. You do precisely model all the message formats because you're really writing an implementation here. So you write the serialization, you write the parsing, you write correctness proofs. You can skip some of these proofs, but they are part of the framework. You can actually verify all of these things. And then you also verify the entire state machine because this is stateful code. You write stateful code which actually maintains the internal state. And the internal state is very important also for security analysis because we allow fine-grained compromise of internal state. This is important for protocols like Signal, where you want to compromise the state after message 2 and then see if message 5 is compromised. Okay, so you really want to allow fine-grained compromise of state to analyze this kind of protocols, and that's allowed in dy star. What do the types look like? Well, the first element of the types and the abstraction that we provide is a notion of secrecy labels. So every key, every data point in dy star, every data element has a label, and the label precisely states who can read this label under what conditions. So this is the label, for example, for the key that comes out of the X3DH protocol in Signal. It looks kind of complicated, but it's as precise as it gets as the exact security of that particular key. Then these labels are propagated through the crypto API. So the crypto API is fully labeled. Of course, this labeling is proved sound within F star itself. And these labels for the crypto API, which is basically a typed crypto API, encode the security assumptions that we have on the underlying crypto. Okay, so it uses secrecy labels and authentication predicates to actually code up exactly what the security assumptions are. But these assumptions are also proof sound with respect to the low-level runtime model. Okay, so what we can do with this, we can verify protocols. Okay, so here's a bunch of protocols that we verified. Of course, the most important part is the bottom line, which is the first mechanized proof of Signal for an arbitrary number of rounds. This is a symbolic proof done in F star at the level of a implementation, which is very, very precise. So this is a symbolic proof for an arbitrary number of rounds for a precise executable implementation of Signal. What is the second thing to note here? The verification time. Type checking is modular. The verification time for these modules grows effectively linearly in the code size. This is very much in contrast to tools like ProVerif and Tamarin, which in some cases can grow exponentially. So for analyzing 2 or 3 messages of Signal, ProVerif can take up to 24 hours to analyze this. Okay, and Tamarin hasn't been used with Signal before, but it will also take similar amounts of time. Whereas with type checking, we can actually kill it in 1.5 minutes. So it's really fast. What is the flip side? Well, we have to annotate the code, right? This is a verification method which requires you to provide detailed type annotations. But how many type annotations is a crucial question. So depending on the complexity of the protocol goals you're trying to prove, the type annotation burden is between 50 and 90% of the model size, of the code size. Okay, so you write the protocol, and then you write the annotations. The annotations are about add another 50 to 90%. So what decides whether you're at the 50 level or the 90 level, it's the complexity of the goal. So for Signal, we have all the goals themselves are recursive. So all the security goals are recursive, the protocol is recursive, and the proofs are inductive. So even to state the security goals and the proofs, there's actually a significant amount of work that happens for those particular recursive goals. And that's what causes the 90% overhead for Signal. But even so, you can see the core implementation is about 800 lines of code and 700 lines of proof, which is perfectly worth it for a protocol like Signal, I think. OK, so that was DY star. So now we have closed the gap. We have verified implementations. We have verified security proofs for the specs, a verified correctness proof for the implementation, all within the same framework, which is F star, coming together to kind of completely close the gap and have a uniform proof. So what's next? What are the big challenges that are left? I think I'm running out of time, so this is my last or second last slide here. Well, the next exciting thing that I'm working on and am excited by is group messaging. So there is, in the IETF, there is a working group called MLS, which is intending to design an efficient, provably secure group messaging protocols. They're trying to repeat the TLS 1.3 experiment, but for group messaging. And what's interesting here is that the groups they're thinking of are huge groups, like 10,000 size groups. So these are the kinds of groups that Signal, WhatsApp, and so on don't do very well with. And so to kind of do this efficiently, almost all the protocols within this suite are tree-based. So almost all the data structures are recursive trees. There are trees for key exchange, there are trees for message encryption. Trees everywhere. So this basically means that tools like Proverif and Cryptoverif and Cryptoverif and Tamarin are going to really struggle with this kind of protocol. But a framework like F star and specifically DY star should be ideal for analyzing this. And so that's what we're using. That's what we're working on. And I'm happy to talk more about this later if anybody's interested. But I should conclude. So in this talk, I sort of tried to give some feeling for what are the things that are what I think has solved problems, what I think has work in progress problems, and what I think has problems for future work. There's actually a lot more than the list I've just given here, obviously. In the talk, we talked about a lot more. But today, if you're using a crypto somewhere in your app, you have, I think, very little excuse for not using verified crypto, because verified crypto is as fast, if not faster, than unverified crypto, and it's widely available, it's open source and so on. Similarly, if you're using a new protocol and you're not analyzing it with Tamarin or Proverif or whatever, I don't know why you're not doing that. But if you're using zero knowledge proofs, MPC, FHE, or post-quantum crypto, then I can understand that this is not yet a mainstream that you can actually use it right now. And of course, in terms of side channels and in terms of making our tools usable by non-verification experts, we have a long way to go. OK, so I'm going to stop there and take questions. I'm sorry if I ran over time too much.
Thanks, Karthik. I think you're totally within time. We stopped in the middle for questions too, so it's great. And we still have up to 20 minutes for more discussion. So here's a question. Emerick Cromhertz asks, did you conclude that NSPK was insecure when attempting verification in DY star? If so, do you have a way to generate counterexamples, or did you build one manually and ensure it was actually a security violation?
So what you can do in the runtime model of DY star is you can execute attacks. OK, so you actually have a way of executing the NSPK attack and showing that actually works. And of course, the proof fails for NSPK. So the proof fails, but it doesn't give you an attack. So we don't have a way of generating the attack. Instead, you have to look at the proof, figure out what the attack is, but then you can write a program that executes the attack and show that this program is well typed. So it's actually a well typed program that succeeds in executing the attack. So indeed, it's a very interesting question on whether we could map these proof failures to attacks automatically, but that's not there yet.
Earlier, Jeremy Epstein had a question. He says, it seems that there's an assumption that hardware that runs the verified implementation runs correctly without introducing any new issues, for example, side channels, through hardware level optimization. Is that true? And if so, how big an assumption is that? Is it realistic?
It's a huge assumption. I mean, I think we have even bigger assumptions in some of this code, which is that the compiler doesn't screw up. which is the false assumption, let's say, not just a big assumption. And the hardware as well, of course, it's currently we have a model in almost all of these tools. We have a model of the hardware, and we trust that the hardware behaves according to that model. And many of the recent attacks, like microarchitectural attacks, fall outside this model. So there is recent work on formalizing and verifying code, and I think you can go look at the thing. I'm not sure it's published, but it'll soon be published, let's say, on how to verify crypto code even against certain classes of like Spectre-like attacks. But even after that, I think there will always be a point at which we are drawing a line and saying we didn't look below that. There could be attacks.
Yeah, I was actually wondering about DY star and ProVerif. I wonder if do you think that there's any prospect for using things like ProVerif to discover some of the annotations needed in DY star, at least for sections of, say, non-inductive proofs?
I think it is possible. I think it could go both ways. You could either use DY star as a way of structuring proofs in tools like ProVerif and CryptoVerif. So I don't know what you would think of as the one outside, what's the one on the inside. So there's an ongoing project with my student Benjamin Lip and Bruno Blanchet, where we are compiling CryptoVerif models to F-star. And the idea being that you have already verified a model in CryptoVerif. How about we generate an F-star spec from it and then use that as the basis of an implementation? Now, the interesting question there is that, okay, if you're just generating the F-star spec as a functional spec to continue from, there's not much else to do. But maybe you want to do more proof in the F-star world, which either were not possible in the CSA in the CryptoVerif world, or just don't make sense in CryptoVerif, but actually make a lot of sense in F-star. So maybe you have some information flow type system encoded in F-star, which you want to nicely compose with whatever guarantees you got out of CryptoVerif. So I think these kinds of questions are very interesting on how these tools can help each other, because clearly we have multiple tools with their own strengths, and we either use one or the other, but we don't have very good stories for how to combine them. And I think DY star provides a good starting point for this for many of these tools, because for tools like Tamarin and CryptoVerif and ProVerif, at the bottom of it, all of the reasoning is done based on traces, and you have a trace semantics on the basis of its stative properties and so on. And I think before DY star, we didn't actually have an explicit notion of traces in many of our analyses, which made linking some of this stuff kind of hard. It was implicit in the tool. It was explicit on pen and paper, but not in the tool. But now I think we have the possibility of even doing some soundness proofs between different analysis techniques within a single framework, which I think is quite exciting.
Yeah, that is exciting. Very, very exciting. I'd love to learn more about DY star. It sounds really cool. Mike Dodd says, this work is so exciting. I'm curious what you think are the barriers to adoption for people using legacy implementations, for example, OpenSSL. What would be necessary to get the majority of people out there using verified implementations?
So I find that there is a lot of interest in verified implementations, and when people ask me about this kind of stuff and that what they should use, I kind of highly recommend that they go look at whatever, depending on their deployment situation. You might be better off using something like CryptoLine or Whale or Jasmine or HACL, and all of these are producing, or Fiat Crypto, they're all producing amazing code. So there is already some good news in the sense that Boring SSL uses a chunk of Fiat Crypto code, and NSS uses HACL and probably EverCrypt soon, maybe not yet. And the Linux kernel uses a bit of HACL code. Beyond that, I think there is a little bit of a cultural shift we might have to make in some of these tools in both ways. So I had a recent conversation with an amazing cryptographer who was saying, he was laughing and saying, listen, I trust GMP code to be correct more than I trust your verification code your verification tool to be correct when it says GMP code is correct, because some code is so well regarded and has been so well vetted for 30 years that people have a high amount of confidence in it. And I suspect in the kernel of Windows and Linux and so on, there's a lot of such code. Crypto code, so to ask people to replace their existing crypto code with yours, I think is a little bit hard culturally and technically, because you have to have a good reason for it. From the research viewpoint, I think a big barrier for us is that we cannot promise to maintain this code forever. I mean, this is just not the setting we have. So I think there is room here for some kind of verified crypto foundation of some kind, or maybe some company like Microsoft or Mozilla or somebody hosting such a project which promises to maintain these things in perpetuity and kind of hires enough verification experts to do this. That will make a lot more people comfortable in accepting this code and pulling it in systematically. So I think that we are still a little bit off there. So whenever you have an enthusiastic developer who wants to use verified crypto, yes, we are able to push things in. But as a structural thing, I think we need to have a bit more structure even on the research side to get this to be systematic. Of course, if you ever get to the place where crypto devs themselves can verify their code, all of this becomes unnecessary because they write the code, they verify the code. So it'll be very, very easy. I'm more optimistic about things like post-quantum crypto, where all the code is new. And the authors of these post-quantum crypto primitives tend to be quite enthusiastic about formal verification. So we may be able to get the NIST and these implementers to actually systematically use formal verification in these new crypto primitives.
Yeah, it's interesting. You mentioned foundations last week or 2 weeks ago at DS3. We had Ashley Williams talking about the Rust Foundation and the dynamics around it. It's interesting to think that maybe some such thing would be necessary for the kind of projects that you mentioned.
Even Signal is a foundation, and OpenSSL is a foundation. So a lot of these things are run like that, I think, right now. But indeed, I mean, it'll be great to have something like OpenSSL systematically take in verified code, not just from our projects, but any of the verified crypto projects. It should also be nice to have Microsoft take some verified code inside the core crypto APIs that are delivered with Windows.
Yes, that would be nice. I think there's some uptake in things like Election Guard and for other kinds of verified code, like verified parsers and so on. So maybe things are moving in that direction. I had one more question, which was I was wondering, for writing crypto protocol spec, I wonder if you think something like hacspec has a role there, rather than writing protocol spec in FStar. Does it make sense to write the spec in some more well understood language?
I think it does. So we've been experimenting a bit with that as well. I think if you really break down, just take the protocol code. Let's just ignore all the API code above it and stuff, because which tends to be very application specific anyway. If you just take the protocol code, then you can see that there is a bunch of composing crypto primitive stuff, which is very easy to do in something like hacspec or any language which you're already using for specifying crypto. Then there is state machines, which are unique to protocols, let's say, and which commonly come up in networking protocols. And there, I think, yeah, it depends on how high level you want to get with modeling your state machines. I think there can be a nice abstraction for state machines in some DSL. We know that there is some work on doing this kind of stuff in FStar, but on the other hand, Rust gives us this nice linearity, which allows us to code up very nice little state machines, at least certain shapes of state machines very conveniently. So maybe again, hacspec is a good candidate for that. And then finally, there's message formatting and parsing, which is like a, I don't know, big part of protocol implementations and specifications, for which you'd ideally use something like everparse, I guess. So if you could find a way of mixing and matching these DSLs that we've already been working on, or other people have been, for doing these specialized protocol-like things and make them available in a spec language, I think that could be very, very useful for sure.
I just want to say lots of thanks pouring in, Karthik. Thank you for that great talk and the perspective on this wide body of work. I learned a lot of things today that I'm familiar with some of the projects, but not with all of them. And it was great to see this overall perspective of things. So thank you for sharing that. And I think similar sentiments are coming in from the audience.
It was a pleasure. I purposely pitched this talk a little bit high in some sense, not showing you what we do, because you can always go read the papers. I hope it worked out.
Thank you so much, and thank you all for attending and for all the questions.
Thanks, guys. Bye.
Bye.